Recording. Yes. Today we are going to continue our discussion of black hole thermodynamics. So in the last section we talked about the Bekenstein-Hawking entropy of black holes. Today, and we argued that the black holes should be, it makes sense if black holes are thermal systems with entropy and so on, characterized by a few macroscopic quantities. But then if so, they have to have a temperature, and the question is what is that temperature? So what we saw was that if we just consider doing some work on the black hole, we see that there will be we'll have a relation that looks like the so we have this relation for black holes that looks like the first law of thermodynamics if we identify some constant times the area as the black hole entropy, and that is the idea of Bekenstein. But in order to determine that proportionality constant, we should understand what is the temperature. So that's the goal of this lecture, to understand what is black hole temperature. And the idea is that black holes are thermal once we consider quantum mechanics. When we look at the quantum fields, then we see that quantum fields on the black hole background are in a thermal state, and we can determine the temperature of them. Okay, so this is the goal. And we want to motivate it. So the first thing to do as motivation, we look at the Schrödinger process. So eventually we want to argue that in a black hole background, particles are being produced in a thermal state. The particles get excited. Now having excitations on a background is something that we are familiar with from QED, from quantum electrodynamics, and that is called Schrödinger process. So what is Schrödinger process? Imagine we have some electric field. So this is something in QED, and we want to consider, well, first let's consider vacuum in QED. So if we have vacuum, we know that in the vacuum we will have virtual processes. In vacuum, there are virtual processes or creation of virtual particles. So we have vacuum loops, which can be thought of as producing a pair of E plus and E minus, for instance. These are virtual particles, so they do not materialize. They do not escape to infinity. They don't hit our detectors. Now the idea is that if you have a non-zero electric field, so if E is non-zero, then this electric field can do the work to make these particles materialize, make them physical, or put them on shell. How does it do it? Basically what we need is that if these virtual particles are produced and separated. Can I ask everyone to mute themselves unless they have questions? Yes, so we have, if you have electric field, then they can work on particles. So imagine we produce this pair of particles and they separate over some distance. Then the electric field can work on these particles over this distance. And if that work is equal to the mass of, to the energy that is required, or to the mass of this pair of particles, then they can become unshed. So we want the work done by the electric field on the particle times the distance to be comparable to the mass of the electron. Now, what is the typical distance for this virtual pairs? The typical distance is the Compton wavelength, which is awarded 1/me. So therefore, if here I put the Compton wavelength, then what I get is that if the electric field is larger than and me squared over the charge of the electron, let me call this E string. So if E is larger than E string, then these virtual pairs can become physical by the work of the electric field. So then what happens is that we will have particle production in the presence of this large electric field. Once we create these particles, then what they do is that they discharge the electric field. So what happens is that our vacuum becomes essentially conductor. We cannot have an electric field which is larger than this threshold electric field. If we go above this threshold, then the electrons and positrons are going to be created, and there will be a current that moves in this vacuum, and then we will just have a flow of charges. So then the vacuum becomes a conductor, and E is discharged. So this is called the Schwinger process. Of course, it can also happen at lower electric fields, but it is exponentially unlikely for the process. While for larger electric fields, then it becomes very efficient. Okay, so therefore, what do we learn from this example is that if we have some external field, then in the presence of external field, we can create particles. Now, let us go back to the Hawking process. So intuitively, Hawking process is similar. The idea is that if we have a black hole, so it is formed from the collapse, then we can have again virtual particles being created in pairs in vacuum. We always have them. But if you imagine that now this pair of particle, antiparticle that I created, they are created very close to the horizon of the black hole. And if one of them ends up inside the horizon and falls into the black hole, and the other one stays outside and escapes to infinity, then we'll have, well, this is a process in which the black hole will emit particles. Or if this process happens, then the one which is outside becomes a physical particle that can escape to infinity. So the intuitive picture is to create a pair of particles near the horizon, such that one of them ends up at the singularity and the other one escapes to infinity. Now, what this process does is that since now we are creating particles which escape to infinity, then the mass of the black hole shrinks. So with time, the black hole loses mass and becomes smaller and smaller. Because the total energy is conserved, as we have learned, there is the ADM mass of the system which is conserved. So if I emit something, then the black hole has to lose mass. Okay, so now we want to do some calculation to determine what is the rate of particle production, or what is the corresponding temperature. So the claim is that this particle production is, these particles are actually produced in a thermal state. Now we are not going to follow Hawking's calculation. I'm going to do something much simpler, just to motivate the idea. Okay, let me here just, maybe I can add a word. So it's the Hawking process is therefore pair production near the horizon, where one particle falls in and the other escapes to infinity. Okay, so now, so the trajectory is a little bit, maybe a little bit windy here. So first of all, I want to show you that when we have a field theory in a thermal state, if we look at the thermal correlators, these thermal correlators are periodic in Euclidean time. Then I use that to, I use the structure of these thermal correlators to show that Rinder observers are seeing thermal correlators, and then we make a connection between Schwarzschild geometry and the Rinder geometry. And from that connection, we determine the temperature. So these are basically the steps that we are going to follow. So the first thing is to consider thermal correlators. And okay, so now first let's consider just the massless scalar. So now consider a massless scalar field in 4 dimensions. So we quantize this field in terms of the annihilation and creation operators. So I imagine you have seen these expressions, just expanding the fields in terms of creation and annihilation operator. This here, HC means Hermitian conjugate. So there we have AK dagger times the complex conjugate of this factor, the mode function. And these A's and A daggers in my conventions, they are normalized. They are normalized so that the commutators is 2 pi cube delta 3 of k minus k prime. Now, first of all, we can ask what is the 2-point correlator of this phi field in Minkowski vacuum. So for now, there is no temperatures, no thermality. So let us just ask what is this correlation function, phi of, and let me look at the correlator at the same position. Then we can use Lorentz invariance to get the full answer once we know it. So what is this object? If I use the commutation relations, then this so I'll have a double integral, but then I use the commutation relation and the fact that A annihilates the vacuum if it acts on it from the left, and A dagger annihilates the vacuum if it acts on it from the right, then I will get 2 pi cube 2k. And then the only factor that remains here will be coming from picking A dagger from this phi and A from this phi, and then commuting them. And that gives a delta function that keeps one of the integrals, and one, I get one factor of e to the minus I kt. So now this integral we can do relatively easily. So this integral over the directions of this momenta k is easy. It just gives us a factor of 4 pi because the integrand doesn't depend on the direction of k. So then overall, this integral becomes 1 over 4 pi squared, integral from 0 to infinity, k dk e to the minus I kt. This I can write as I over 4 pi squared dt of the integral from 0 to infinity dk e to the minus I kt. Then I introduce some I epsilon prescription for this integral to converge. And then the result becomes minus 1 over 4 pi squared times t minus I epsilon squared. Now we can use Lorentz invariance to conclude that phi of t and r and phi of 0 and 0 is equal to minus 1 over 4 pi squared t squared minus r squared minus I epsilon. So here I just wrote the Lorentz invariant combination that reduces to our original answer. If I set the positions to be equal. Okay, so this was just the 2-point correlator in vacuum for a massless scalar field in 4 dimensions. Now we want to consider any questions so far?
I have one question. So in this correlator, are we using normal ordering?
No. No, I didn't. If I normal order, what is normal order? Normal ordering puts all annihilation operators to the right of creation operators. So if I did that, I will get 0. So no, it's not normal. It's just a no. This is sometimes called white man correlator. There's no, the ordering is as written. Okay. Did it answer the question?
Yes.
Okay, thanks. Other questions? All right, so now we want to turn on the temperature. So now we want to have non-zero temperature, which now I also talk about inverse temperature beta. So beta is 1 over T, and it is not 0, neither infinity. Okay, so what happens at non-zero temperature? At non-zero temperature, we have thermal occupation, non-zero occupation number. So if I look at the expectation value of the number operator, so now here it would be a bit nicer if we worked at finite volume so that the momenta were discrete. But I'm going to continue working in the continuum. So the expressions might look a little bit cumbersome, but at the end, the results would be the same. So if I look at this expectation value of the number operator, then I will have the usual thermal factor, the occupation number, e to the beta k minus 1 times the delta function, the momentum conserving delta function. Now let me mention just in parentheses, if at finite volume, what would happen is that this 2 pi cube delta 3 of k minus k prime would go to L cube. Say we put it in a box with size L, size of each side to be L, then this will be just the delta of k, and K prime, and then the integers d3k over 2 pi cube would go to 1 over L cubed sum over K. But no other dramatic change. Okay, now let us use this relation to ask about the correlator, the thermal correlator, again at equal time, T0, phi 0, 0, but not at finite temperature. Now, if I look at this now, there will be additional terms in this expression. So maybe I can write it more explicitly, d3k, d3k prime, 2 pi to the 6, the square root of 2k, the square root of 4k, k prime, and then we will have ak prime dagger e to the minus ikt plus ak dagger ak prime e to the ikt. Oh, and these are the magnitudes. Okay, so now we use that relation that we had to obtain the following result. So there will be a term which looks like what we had before, just from the commutator. And then there will be additional terms. So the terms that we had before is e to the minus ikt. And then the extra terms are coming from the thermal occupation, which looks like e to the 1 over e to the beta k minus 1. So this is the thermal occupation times e to the minus ikt plus e to the plus ikt. Now, this factor, this thermal occupation number, this can be written in a more useful way for our purposes. In fact, that's how it arises in the first place when we compute the thermal partition function. So this, let me use a different color. So if we look at 1 over e to the beta k minus 1, this we can write it as sum over n from 1 to infinity e to the minus beta n k. So just the geometric series. Now, if I plug this in this expression, then we will get a sum so our correlator will be d3k over 2 pi cube times 2k. And now I will get a sum from minus infinity to plus infinity. over e to the minus beta n k and let's see a second. Actually, I have to do something before, so this is not correct. So I actually plug this in there and first do the integration over k. So the integration over k is simple. It's kind of similar to what we did before, integral over some exponential. So let's look at one of the terms in this sum. So one of the terms would look like there will be a factor of e to the minus beta nk. Then there will be minus or plus I kt. So this integral looks similar to the kind of integral that we did before. So the result of this is again so we do that the angular part, it reduces the factors of pi to 1 over 4 pi squared, and then from the integral over the length of the k we get what we get beta n plus minus it squared. So in particular, if I set n to 0, if I set n to 0 or beta to 0, this reduces to what we had before. And this is the answer. So this part will be 0, and I get minus 1 over 4 pi squared over t squared, which is what we had before. So if you remember here, that's what we get. Okay, so every term in this expansion, so I plug this in here, and then I do the integral over k. So therefore, eventually what we get for this correlate of phi of t and 0 and phi of 0 and 0 is now 1 over 4 pi squared, and then there will be a sum over n from minus infinity to plus infinity, 1 over beta n plus I t squared. So I just rearrange the term, and all of them combine together to give me this sum, which I can also write it a little bit in a bit more useful way by in the following way. I can factor out beta squared and I from this, and this becomes 1 over minus 1 over 4 beta squared, sum from minus infinity to plus infinity, 1 over t minus I 1 over t over beta pi t over beta minus I n pi squared. So I also took these factors of pi inside. Now, why do I rearrange it like this? Because now this expression has a property that that I like. So this has poles. It has double poles when t is equal to when t becomes n beta, or when this argument, this whole object becomes a multiple of I n times a multiple, an integer multiple of I pi. So this kind of functions is called, it's just a sum of poles, and I can find another function which is analytic, except that it has the same structure of poles, and then that would be the resummation of this this sum. So what is that other function that has the same structure of poles? It is the sinh function, sine hyperbolic, because if I take sine hyperbolic and evaluate it along the imaginary axis, then it becomes a normal sine function. And sine function is zeros, has zeros at when its argument is equal to n times pi. So if I have 1 over sine hyperbolic squared, if I consider this function 1 over minus 1 over 4 beta squared sinh squared of pi t over beta, this will have the same structure of poles, and then you can check that it has the same residues. And then this is the property of meromorphic functions. If I match all of the poles and the residues of the poles, then they are the same object. Or essentially, this function is just determined by this sum over the poles with the right residues, which is this sum. Okay, so we obtain this result for the thermal correlator. What does it? What property does it have? It has the following property, which is what I needed. At least one of the properties that I needed. Of course, it's also obvious from this expansion that we have here. The thermal correlator is periodic in Euclidean time. So if I send t to I times, so if I send t to I times t Euclidean, then the statement is that it is periodic under shifting the Euclidean time by the inverse temperature beta. And that's the property of this this solution that we found. Okay. Well, of course, we learned it in one particular example, but this is a general fact about thermal correlators. Which can be proven in using for instance, using the path integral formulation of quantum field theory. Okay, any questions so far? All right, so we are almost there. So now what I do is to next consider the Rindler observer in Minkowski and ask what is the correlator of the field that the Rindler observer measures. So let us go to a new page and consider Rindler observer. So what is who is the Rindler observer? So we consider Minkowski spacetime. In particular, I just focus on one plane, a TX plane of that, and look at the light cone here. Not a very good light cone. And then I consider an accelerated observer here. So there is an observer along this line. It's the proper time of this observer. We call it tau, and so along the trajectory of this observer, t is equal to, and let's say that it has acceleration alpha, which is related to the intercept with the x-axis. So t is 1 over alpha sinh alpha tau, and x is 1 over alpha cosh alpha tau. And tau is, I chose the origin of tau to be 0 when we start at t equal to 0. Okay, now let us ask what is the correlation function of the field. So say we consider just a Minkowski correlator. So we assume we have a field. This is an observer who moves in Minkowski spacetime. And imagine there is a field here. So we have this phi of t and x in this spacetime. We know we calculated the 2-point function of this field for any 2 points. So now we can ask what is this 2-point correlation function along the trajectory of the Rindler observer, right? So therefore, I look at phi of t and tau and x and tau. So other components are 0, even though we are in 4D. I only write the 2 components. And then t of 0 and x of 0. So I'm looking at correlator between these 2 points. So this object I want to give, maybe we can give it a name. This is the correlation function for a Rindler observer. So maybe we can, let's give it some name. So this is phi of tau, phi of 0, Rindler. But how do we compute it? We just plug it in the expression that we had, right? We had the expression in the Minkowski vacuum for the 2-point function. Remember, here we are just in Minkowski vacuum. Just the observer is moving along some trajectory. We have an accelerated observer. So the general expression that we had was t1 minus t2 squared minus x1 minus x2 squared, right? The Lorentz invariant combination. So t1 minus t2 is the whole thing. It gives me a factor of 1 over alpha squared, and then t of tau is sinh alpha tau, and T of 0 is 0. So I get sinh squared minus x of tau gives me cos alpha tau. Remember, I factored out 1 over alpha, so this gives me cos 1 over alpha cos alpha tau, and the 1 over alpha I factored out. And then x of 0 is just 1 over alpha, because cos of 0 is 1. So this gives me cos alpha tau minus 1 squared. And this expression is, so what is it? This is minus alpha squared divided by 4 pi squared. Now, if you manipulate a bit this denominator, what we get is twice cos alpha tau minus 2, which is minus alpha squared over 16 pi squared sinh the squared of alpha tau over 2. Okay, so now this expression, which is the 2-point function of the field measured by the Rindler observer, we should compare this with the expression for the thermal correlator, with this expression. And in fact, let me do this. So this is our thermal correlator. We want to compare it with the result for the result for the Rindler observer, and then this comparison tells us that the Rindler observer measures the thermal correlator with temperature, or inverse temperature beta Rindler equal to, let me write the temperature. With temperature equal to, so beta should be 2 pi over alpha. Therefore, temperature is alpha over 2. So this is T Rindler. Now, of course, this T shouldn't be confused with this T. This time was the time that we used in the thermal system. So here, this T has to be identified with tau. Any questions so far? Okay, so what do we learn? What we learn is that in Minkowski vacuum, of course, if we have inertial observers, if they look at the correlators, they see just the normal correlators in vacuum. But if we consider accelerated observers, then they measure excitations. They see particle excitations. This is called the Unruh effect. This fact that we see excitation or non-zero temperature is called the Unruh effect. And this particle production is exactly thermal, with the temperature related to the acceleration of the observer. And of course, if I send the acceleration to 0, this temperature goes to 0. Okay, so now, if there is no other question, then we are very close to understand why we have a thermal state or thermal excitations in the presence of a Schwarzschild black hole. So now we consider Schwarzschild black hole. Okay, and then let us focus on the near horizon geometry of the Schwarzschild black hole. The goal is to show that the near horizon geometry of a Schwarzschild black hole is identical to the Rindler space. And from this similarity, we determine the temperature. Well, perhaps, anyway, let us continue this. Maybe I could have said something before, but it doesn't matter. So so let us, all right, focus near the horizon. So we want to go near the horizon. So let's write R equals RG plus X, where X is much less than RG. And expand the metric for a small x. So then we have the near horizon metric, which will look like, so what do we have? We have RG over RG plus X. So this gives me, a factor of X over RG dt squared plus dx squared RG over X plus, now in the radial part, so as you see, this T and R part of TT and RR part of the metric become singular or 0 when I send x to 0. That doesn't happen to the spherical part of the metric. So there I can just ignore x. Now let us choose a different variable to make this part normal. And the reason why I'm doing this is because I'm going to show you that this part of the TR part of the metric becomes the same as the what is called the Rindler metric. That yeah, that's the thing that perhaps I should have said before. Maybe you have seen it, but if not, I'm going to tell you what the Rindler metric is soon. But so I want to make this TR part of the metric to look kind of familiar. So what do? We want the square root of RG over X times dx to be some new coordinate that I call it this curly R, which means that R is, so this is different. This is a different R compared to the usual short-sheet R. That's why it looks different. So what would be R? If I want to solve this, it will be twice the square root of RG times X. Right? If I take the derivative of this, then I will get this expression. So from here, then I conclude X is equal to R squared over 4 RG. And then the metric in this coordinates is going to look like this squared equals approximately equals minus R squared over 4 RG squared dt squared plus dr squared. Okay, and then I don't care about the spherical part much. I only care about this part of the metric. Okay, so now I keep calling this the Rindler metric. Let me just remind you what the Rindler metric is. So this is what I call Rindler metric. So the Rindler metric is just a reparametrization of the Minkowski metric. So if we go back to Minkowski, it's a reparametrization of the Minkowski metric using the times of the Rindler observers. That's why it's called a Rindler metric. So, and it covers only part of the Minkowski diagram. So if I say T is equal to R times sinh tau, and X is equal to R times cos tau. So now you see the similarity between this and what we wrote for the position and time of a Rindler observer. So if I plug this in the Minkowski metric, so if I take ds squared equals minus dt squared plus dx squared, then this goes to ds squared equals minus r squared d tau squared plus dr squared, right? So I'm just taking these expressions for t and x and plug it in here. I'll get this metric. So this is what is called the Rindler metric. And what I'm claiming is that the near horizon geometry of the Schwarzschild, if I look at the TR part of it, it is the same as the Rindler metric. If I do a redefinition of this time variable. So now in particular, this Rindler metric has, if I here I send R to 1, then that would correspond to the trajectory of an observer who has acceleration alpha equals 1 in the previous example that we considered. Now, how do we determine the temperature? So this tau, therefore, this tau is actually measuring the time of that particular observer. So if I consider other accelerated observers, the time that they measure are related to tau by some rescaling. But the one at r equals 1, at x r equals 1, which has intercept x equals 1, is the one that who is measuring this tau as the proper time. So how do we determine the temperature of this? So we had one way of determining the temperature. We just looked at the correlator of the field, and we saw that it matches the thermal correlate. So one other way to look at it is that if I take this metric, Rindler metric, and then analytically continue tau to I tau, then my metric becomes r squared d tau e squared plus dr squared. And now this metric, if I want it to be regular at r equal to 0, so this metric, you notice that this is essentially the same metric as the metric on the metric of a plane in radial coordinates, right? If you think of this tau e as an angular variable, this is just dr squared times r squared d phi squared, for instance, if phi was an angular variable. Now, if we want this space to be, this Euclidean space to be regular, then we have to say that this tau e is periodic with periodicity 2 pi. So regularity of Euclidean Rindler space implies tau e is periodic with periodicity 2 pi. Now, remember that periodicity in Euclidean time, we showed that this periodicity in Euclidean time is related to the inverse temperature. So therefore, we conclude that beta should be equal to 2 pi, which is actually the temperature of a Rindler observer, which has intercept 1. So if we chose another intercept, then we would get a different periodicity, which would exactly match what we obtained before. So now here, we apply the same logic, right? This is this near horizon geometry is a Rindler space. We go to Euclidean time. So t, we send it to tau, Euclidean t, and ask what is the periodicity of t, so that we have a regular metric in Euclidean time, and then that periodicity will give us the temperature. So we apply the same logic to near horizon limit of Schwarzschild. So here we are dealing with this metric. We take T to I Euclidean TE, so then we get ds squared Euclidean is equal to minus r, no, there's no minus, r squared over 4 rg squared dte squared plus dr squared. And from here we conclude that the periodicity in Euclidean time for this geometry to be regular is so let's see, it should be if I absorb this factor inside TE, then the periodicity should be 2 pi. Therefore, periodicity of T Euclidean should be 4 pi Rg, which means that the temperature, the Hawking temperature of the Schwarzschild black hole is 1 over 4 pi Rg. Let's see if I got it correctly. Yes. Okay, so this is the main result of this lecture. Other questions?
One question. So we saw that near horizon, the Schwarzschild metric, we can transform it into something similar to Rindler metric. And we know that Rindler metric, we can transform it to a Minkowski metric. So it turns out that the Schwarzschild metric at near the horizon, we can approximate it to a flat space-time. So, I mean, how do we see it quantitatively? I mean,
oh, actually, it's not the case that you can make the full Schwarzschild metric. You can make it to look like Minkowski, because of the parts that I was not very interested in, because of the spherical part. So if what is the difference between Rindler and Schwarzschild? In the case of Rindler, this extra, we call it transverse directions. These extra transverse directions in the case of Rindlers are just planes. And then the full metric becomes equivalent to Minkowski. While if the transverse direction is a sphere, then it is not It's not the same as Minkowski. The only thing that we used here is that we used the fact that in order for, when we go Euclidean, in order for this factor to be regular, we need to impose periodicity in Euclidean time. And that periodicity determines the temperature. So that's why we made the connection with, well, in principle, I didn't need to even make connection to Rindler. It's just that for this metric to be regular in Euclidean time, we have to impose this regularity. But it's useful to know that near the horizon, we have a Rindler geometry. At least in this, the TR part of the metric is Rindler, while globally it's different from Rindler.
So we can say that if we consider some Riemann curvature tensor with indices only zeros and ones, we will get something negligible zero.
Oh, even that is not obvious. Probably not, because Riemann curvature has inside it has some over also transverse directions. So it's not that Riemann curvature with only zeros and ones depends only on the part of the 0-1 part of the metric. Other questions?
I have a question too. So we found the temperature near the horizon, right?
We found the temperature using the near horizon geometry.
Yes, I mean, is it like a particular example? I mean, like, can we do it like in the center or something like that?
You said in the center?
Center, or I don't know, I mean.
Center.
Yes.
I
mean, is this like a particular example?
Well, it is a particular example. So in the case of in the case of the Rindler, I guess we were considering yeah, let me see. So here, for instance, R going to 0 would mean that we get to the horizon, right? Because if you remember, there is a relation between X and this R, this curly R. and x was the distance from the horizon. So if I send x to 0, r becomes rg. So we are at the horizon. So this curly r would be, if I send that to 0, we will be at the horizon. So what we saw is that here, if I want the Euclidean metric to be regular at horizon, at this r equal to 0, then that imposes some periodicity in the Euclidean time, which gives us the temperature. And then there is a similar story in the case of Rindler observer. If I want the Rindler metric to be regular at the Rindler horizon, when I go to Euclidean time, then again I will get a periodicity which corresponds to the temperature. Now, how general this is? Well, this idea that you can go to Euclidean and determine, to Euclidean time and determine temperature by asking whether for what choice of periodicity the Euclidean geometry is regular. Asking about regularity of Euclidean geometry, that is not always possible. Like, for instance, in the case of Kerr geometry, I don't know how to do this, how to determine temperature from an argument like this. But this does not mean that the Kerr geometry is not thermal. Also for the Kerr geometry, we can determine the temperature, but using other methods. I don't know if I answered the question.
Yeah, thank you. I mean, I was just thinking we can find like find the temperature like generally, but I mean, I understand what you say.
Yeah, I should emphasize that it's not that every space-time has a temperature. This is like, for instance, Minkowski has 0 temperature. Or if I just consider a neutron star, then there could be non-zero temperature because of the state of the matter fields of the neutron star, but not because I have a geometry that imposes some non-trivial temperature.
Thank you.
Let me say it this way. Temperature is a property of the state of the system. So we say, for instance, we are in the thermal state. Say if you have a quantum field theory, we can have different states of the system. Now, the statement in the case of, for instance, say Rindler, that's easier case. So what do we say in that case? We say the state of the system, we fixed it to be the Minkowski vacuum for the field. Now, if I am an accelerated observer and I fix the state of the system as I said, then I, as an accelerated observer, I did measure a non-zero temperature given by my acceleration divided by 2 pi. In the case of black hole, the statement is that if I fix the state of the system by some regularity condition at the horizon, then that uniquely fixes the matter fields to be at some finite temperature. But for instance, if you have a neutron star, the state of the system is not fixed by anything. The matter fields in a neutron star, they can be in different states with different temperatures. So it's the simplicity, the fact that we are talking about a vacuum solution that allows us to have a preferred choice of the state. That state is actually called the Hartle-Hawking state, and that has a non-zero temperature in the case of Schwarz. Other questions? Okay, maybe let me just mention some consequence of this, having a non-zero Hawking temperature, having a non-zero black hole temperature. What this means is that black holes evaporate because they produce particles and they lose mass, as I mentioned. So eventually they lose all of their mass, assuming that this computation is valid all the way until they become very small, Planckian. But even if the picture completely changes at that scale, it means that they evaporate until they are not semi-classical anymore, and then we cannot trust this computation. But still, it leads to a somewhat dramatic picture, which is that the Penrose diagram of the black hole geometry that we used to be drawing, that was actually the classical picture. So this black hole that was formed from the collapse. So this was the classical picture. Quantum mechanically, what happens is that this black hole will evaporate, and then we will be back to asymptotical Minkowski spacetime. And then there will be Hawking quanta. Yeah. Or you can draw Hawking quanta like this. Or Hawking radiation. And the thermality of this Hawking radiation leads to interesting puzzles when we try to put together quantum mechanics or quantum field theory and general relativity. Okay, if there is no other question, then we will reconvene on Friday. So there won't be any lecture tomorrow. We can have, if you have questions, then feel free to stop by during that time or other times. Okay. Bye. Thank you.
Thank you.
Thank you.
Thank you.